right, this is Physics, Chapter 6, Lecture 3B. We're going to be working an on-your-own problem on page 205. It's the last page of your notes, the very back on page 6. And what I want you to do is, we're going to do on your own 6.10 first, but don't take up this whole back page with that because we're going to rework that problem with some different parameters. So try to take up no more than half on this. Now what we're doing, we're doing a chapter 5 problem on steroids. We're applying Newton's second law to more than one object. Okay, so let's look at the on your own problem on page 205. So it says a girl is dragging two boxes, 322 kilograms and 245 kilograms. So those are crazy numbers. I mean, this girl has quadriceps the size of a gorilla. Those two boxes together are way over 1,000 pounds. But anyway, the two boxes are attached to each other with a thin string that can only withstand a tension of 45 newtons before it breaks. So numbers really don't make any sense here. You'd want like a steel cable in between the two, but we'll use what the author put in here, 45 newtons before it breaks. What is the maximum force that the child can exert with her bike without breaking the string? And we're going to ignore friction. In this one, we're going to ignore friction, but that's not very practical, is it? So I'm going to change this to include friction on when I work it again. But first, let's work it like this, where we ignore friction. So what we want to do is draw a free body diagram with both boxes. Okay, so let's draw the box that's in the rear. It's 245 kilograms. And since there's friction, so we don't have to put a force this way since there's no friction. So we've got the tension in the string, and that is 45 newtons. Okay, so that's the rear box. So the front box, free body diagram there, it's 322 kilograms. We have the force from the bicycle, the force of the girl. That's what we're trying to figure out, provided by the girl. But we also have the string pulling against that box. Okay, this way. So that would be also 45 newtons going to the left. So we're just going to analyze each box independently. So we have the sum of all the forces is equal to the mass times acceleration for the rear box. Okay. So that's going to be 45 newtons, that's the only force, is equal to 245 kilograms times acceleration. So acceleration will be 45 newtons divided by 245 kilograms. If you put that in your calculator, it's 0.184 meters per second squared. Now that's also going to be the acceleration on this system, because they're tied together, right? So they have to since they're tied together with the rope, they're going to accelerate the same at the same pace there. So let's look at this box. Sum of all the forces is equal to mass times acceleration. We do have one more force this time, but we know acceleration. So I've got F pulling to the right, this right here, big F, minus 45 newtons is equal to 322 kilograms times the acceleration. Well, I know what the acceleration is, don't I? It's 0.184. Okay, so our force is then going to be, let's move that negative 45 to the right. It's going to be 45 plus 322 times 0.184. So the force of the girl is 104.2 newtons. Now, there's no friction, So, the problem isn't very real world, but that's how you would work. So you've got really simultaneous equations here, two different equations, and we solve for A, and then we can plug that in the other equation and get our unknown. Now, that problem is good enough for the problem like this in the practice problems. However, it's not good enough for number 10 on the extra practice problems. So I want to go ahead and use this same problem, but apply friction to it. So let's call this 6.10b, and it is right on your notes for extra practice problem number 10. So let's change a few things. So we've got the same situation with the girl pulling the boxes, but this time I need to change that tension to a higher number. All right, because if we introduce friction, then that's a lot more force. So the tension in the string, let's say, is 500 newtons. That's the maximum before it breaks. And mu sub k is equal to 0.1. So that's the only two things that we're going to change. And let's now work this problem again. Let's look at the rear box. Do a free body diagram. That's 245 kilograms. We know that we have a 500 newtons force going to the right, but we also have the force of friction going to the left. We can get friction, but we've got to get the normal force, don't we? And the normal force is just equal to the weight, isn't it? So we know that weight is equal to mass times gravity. That's 245 kilograms times 9.8 meters per second squared. So the weight is 2,401 newtons. Right? And normal force is equal to the weight because there's no angle. So that's equal to the normal force. Now we can get friction. It's mu sub k times the normal force. We said mu sub k is 0.1. which of course is way too slick, but 0.1 times 2,401 newtons. So the force of friction is equal to 240.1 newtons. So if the sum of all the forces on this box is equal to mass times acceleration, I'm going to have 500 newtons to the right minus the force of friction, 240.1 newtons, is equal to the mass, 245 kilograms, times A. So A is equal to 500 minus 240.1 over 245. And that is going to equal 1.06 meters per second squared. Now that's not what it asked for. If it asked for acceleration, you would be good. But we also need to now analyze the front box so that we can get the force. So the front box, it's 322 kilograms. So we've got the force of the girl pulling that way. We have friction. And we also have that 500 Newton force on the string pulling against the front box. Where this is the front box. So I've got the normal force and also the weight. So weight is going to be 322 kilograms times 9.8 meters per second squared. Right, so the weight of the front box is 315.6 newtons. No, I don't have that right. Let's see. It is 3,155.6. All right, sorry about that. 3,155.6. So friction is equal to mu sub k times the weight or normal force. So this is also equal to the normal force. Remember, and that's only because there's no angle. If there's an angle, then goodness, we could do it, but it would be pretty complicated. So 0.1 times 3155.6 newtons. So move the decimal place one spot. You have 315.6 newtons. So that's where I got that from. So friction is 315.6. All right, so the sum of all the forces is equal to mass times acceleration. So the front force, F, provided by the girl, minus 500 newtons, minus frictions. We've got two forces pulling to the left, minus 315.6 newtons, is equal to the mass, 322, times acceleration, which is 1.06. All right, I don't have room for the units. Sorry about that. Not good space there. But 1.06 meters per second squared. So the force of the girl is going to be, let's move the 500 and the 315.6 to the right. 500 plus 315.6, so 815.6, plus 322 times 1.06. All right, so the force is 1156.9 newtons. All right, so over 1,000 newtons more, and basically 0.1 would be the friction coefficient of friction for like watered down ice. I mean, super slick, you could barely walk on it, and just having any friction at all added 1,000 newtons. A normal asphalt road would have a coefficient of friction around 1. So that would multiply this force by a factor of 10. So, you know, you'd be looking at over 10,000 newtons on a normal asphalt road. And so, you know, that's why this isn't a practical problem. All right, let's look at the homework, and it's just finishing out the Chapter 6 review questions and practice problems. So the homework for both Lecture 3A and 3B. Review question, there's only one left. All right, so that's page 214. You can do number 10. And practice problem page, going to flip over to 216. And you can do 8 through 10. So that does it for the lectures in Chapter 6. We'll move on to the extra practice problems for both Chapter 5 and Chapter 6. And then we'll have our test. All right, have a great day.